So in the last talk, you learned how to get access to Fukaku, yeah, and how like starting up a terminal so you can start giving commands to a computer. And like this talk and the second half tomorrow is about how can I write my own programs to run on that computer. I guess some of you have already written programs in C, Python, or something to run on your laptop, but running on such a big system like Fukaku, because it has more than one processor, it's a little bit more special, a little bit more complicated. And this is basically what the presentation is about. I will teach you one method which works on all parallel computers, on all clusters, which is called MPI. And then I will give you a shorter lecture also on OpenMP, which is about when you want to just use like one node of a computer. So we have about 3 hours for that. Normally, in my home institution, when we give an MPI class, it's 3 days, 4 days, or 5 days. So don't expect, when you basically tomorrow, that you are an MPI expert and can write programs yourself. We don't have that time here at the school. It's more about that you know what is this all about. What is the most important concepts of doing it. So when you basically are at home, you find online tutorials or so, you have already a start. The second thing we want to do tomorrow afternoon is we will actually do it. Yeah, like in the morning, today and tomorrow morning is just like we talk about it. And then tomorrow in the afternoon, we have another 3 hours. You will be able to write a little program and run it on Fukaku and see it going. So by the end of tomorrow, I promise that each of you will have run a program successfully on Fukaku. You might think, what is this? Is it special? I mean, it's just a computer. But Fukaku is so expensive and so large, so far, less than 10,000 people in the whole world have used it. So when you have done it, you are part of a top 10,000 people in the world who have used Fukaku. You are then very special people. Okay. Okay. So this is basically where we start. So I will basically first, yeah, we need to establish some terminology. If I say that word, you need to know what it means. Yeah, so I first tell you the most important words and give you a rough introduction. Then high performance computing, there is a P in it. And P stands for performance. It's not only writing a program, but you want to write a very efficient, fast program because it's high performance computing. Yeah, so we need a little bit to learn about what does it mean, high performance. And then I talk to a little bit how computers look like, what this implication that has for programming and so on. And then I show you some examples. You will see Fukaku on Tuesday, but there's many more interesting systems in the world, like I show you some examples. Okay, let's get in. So what is high performance computing about? Yeah, so you know in the past it was like this, that there were people doing theory, yeah, coming up with new ideas, models, hypotheses and so on. And there were people in laboratories doing experiments. It was just, and when the experiment people try to prove the theories of theoretical people and so on. Now there is many parts of science where you cannot do laboratory experiments. Think about astronomers. They cannot take a spaceship, fly to some galaxy and make experiment, or people working on viruses or in very small molecules. So over time, what they did is they took this theoretical model and said, okay, let's try to simulate that in a big computer. So they make simulations about it. And now meanwhile, more and more people are doing this. And then we use AI to analyze all the data. And this is called computational science. And meanwhile, people think this is kind of like the third part of science, yeah, like theory, practice in computational science. And there's many, many challenging applications, and I don't need to talk about because Satoshi in the morning showed you many, many examples, yeah, like climate, virus, engineering, and so on. Problem is, when you do that, like if you make it, you want to have the results as realistic as possible, which means you have to do a lot of computations. And you have to use a lot of data. So you need a computer which can run a lot of calculations and have a lot of memory to store all the data. As I said, there's many examples. If you want to look, like at some point I was responsible for running an HPC Matters campaign, so we produced a lot of little videos, like 3-4 minute videos, to show interesting examples. Yeah, and it's not just the usual things like aerospace and climate change, but I remember, like here, we also had something about diapers. Like, how does supercomputers help with diapers? Watch the video; it's very interesting, and so on. Okay, so what is a supercomputer? There is not a simple, easy explanation, but basically what it means, you take the most powerful computer and the most effective computer at the current time, and that you call it a supercomputer. So this supercomputer in 10 years might not be a supercomputer anymore because there are more powerful ones. And we did it, it's not like at some point you have a supercomputer, and then the next more powerful is called hypercomputer, and the next one is called whatever. Yeah? So we always said supercomputer is the most powerful system currently. And when you look back, it was way before your time, but it was, I'm so old, I was still there. So in the 1980s and 1990s, these were very special vector computers in large boxes, like you heard the name perhaps like Cray or CDCs and so on. But only like government and with a lot of money could buy and own such a computer, never a university or something like that. So in the 1990s, the government says, we don't want to spend all that money on all these big expensive computers, we need to find a cheaper way. And so what people did is said, okay, one way to make things faster and more effective is, instead of basically doing it with one thing, I use 10 things. It's like, yeah, when you want to move, you ask a few friends, and then it goes quicker, yeah, because like yourself, you would have to go up and down the stairs all the time, but if you have like 10 friends, like 2 people are packing, 2 people are getting it down to a car, a few drivers over, and the other 2 people pack it up. So you have 8 people, and we get it done much faster. And you did hear the same idea. You go to a computer store, like in US it's called Best Buy. I don't know how it's called here in the Asian area, but there's where you can buy normal computers. Yeah, like in the worst case, you get just some laptops, and you buy them, and you buy a network switch, and you connect them together, and then you have a little parallel system. And this is what people did in the 90s. And because these pieces, like laptops, get produced in the millions, they are cheap. Yeah, and also the network is cheap. So this way made it, you had like large, complicated things with many pieces, but it was much, much cheaper. Yeah, and I compare that to basically, you need to like do mining, and you have to dig like a big hole. And what, like before that, you had to build this really complicated machines. Yeah, like this machine is 200 meters long, 100 meters high, and there's only like 10 in the world. But doing it the new way is like, oh, I just get a lot of students who because they're cheap, and then give them some shuffle and thing, and then if I get enough, I can also make a big hole. Yeah, of course, if you have more time, you can also do it like this. Yeah, you get laser machines, and you don't need so much. It depends on your budget, how quick you have to be done, and so on. But the idea is always you take many of the same thing working together. Okay, so why should you learn that? You say, okay, some people care about that, but why should I care about? One thing is, yeah, a parallel computer can be the only way to achieve a specific calculation, yeah, in a given time. So it could be that your laptop is too slow, and you use these multiple processors to do the calculation faster, or your laptop is too small. It doesn't fit all the data you need to calculate, so you need multiple computers that you have more memory, and you can use, like, store all the data. But most of the time, it's both. Okay. Then, and you probably know, meanwhile, these slides are a little bit getting older. Meanwhile, your laptop is probably a parallel system. It's a quad core, so it has 4 cores, which is like 4 parallel system. Your smartphone is typically at least 4 or 8 cores. So even your smartphone is a parallel computer. It's not a supercomputer, but it's a parallel computer. So if you want to program them, and you want to use all the cores in your smartphone and all the cores in your laptop at the same time, you can do what I tell you in a minute. Okay, so parallel computing basically means I'm solving one specific task. I do, yeah, a specific astronomical galaxy simulation. And I use multiple processors at the same time, simultaneously. So I use the same time all processors to do one thing. And these multiple processors and all the disk and something are part of one, I don't have a good word, of one architecture. So they fit in one room, or in a larger room in case of Fukaku. But they are all together. Then you call it parallel computing. There's also distributed computing, and sometimes people call that grid computing. This means, again, I'm doing one task. I use multiple processors, but they are distributed all over the world. So it's a little bit like World Wide Web. Yeah, so if you go to YouTube, you use your laptop, it connects to a Google server, which spreads out to a Google disk system, and they use all these things together to very quickly give you a video. But this is distributed computing because it uses multiple computers in more rooms at once. I mean, it's computing, the computers are in one room. Then there's a specific notion you sometimes come across, embarrassingly parallel. So you do something in parallel, but it's extremely simple. And you kind of said, you're embarrassed by it because it's so simple. And it means when you have to do thousands of things, small things, but they're all the same. Yeah, thinking about sending 100,000 letters to people in your country. Yeah, and so each send is the same, and they don't depend on each other. So you can use, like, say, 100 students, and each can do it without talking to the others. And this is, of course, very simple if you have something like this on a parallel computer. So if I said, I have to 10,000 times calculate something specific just with different parameters. You just take these calculations, throw them on a different cores, and they don't have to talk to each other, they just work. So this is simple, but unfortunately, most calculations and simulations are not that simple. So, and then supercomputing means I use the fastest and biggest machines to solve really large problems. Yeah. So this is more than parallel. Distributed means I'm doing in parallel. Supercomputing means I use really big and really fast machines. So what is now high-performance computing? High-performance computing, sometimes people use it in the same way as supercomputing, but high-performance computing, typically people mean a larger ecosystem. So again, you're using supercomputers, but you also have fast networks, you have a large storage, you have post and pre-processing devices, visualization to solve like really, really interesting problems. But it's a little bit fussy here. So it's depending whom you talk to. Some people say supercomputing, some people say high-performance computing. Some people say high-performance computing is as soon as you use multiple computers at the same time. But high-performance for me always means, yeah, performance. So it should be like very fast, very efficient. Okay, from Kathy, but also from Satoshi, you heard now everything is AI. Okay, I'm not so sure about that. Yeah, so one thing is true, that no one is debating that. Artificial intelligence is just one example how to use a computer. Yeah, so you can do astronomy, you can do math problems, you could climate, and AI is just another way to use a large computer. But artificial intelligence is a very wide field. So yeah, like what most people talk about when they talk about AI now, they actually mean, so there is a subset of artificial intelligence, it's called machine learning, ML. And then if you're using special techniques of machine learning called deep neural networks, or when basically when it's about learning, it's about deep learning. So this is actually the AI which needs these really large supercomputers. And this is because, yeah, most people, yeah, basically they say artificial intelligence, but they actually mean deep learning. Yeah? So when you look at deep learning, this training of these large language models and foundation models requires enormously very large, so we read the whole internet into your computer to learn about it. So it's very data intensive. And it requires a lot of calculations to do this training. So they have to use a supercomputer for 3 or 4 months to generate a model. So it's compute intensive, but it can be parallelized very easily. So this is why it's an HPC application. Yeah? So artificial intelligence is only successful because very quickly they found out, oh, there's these big supercomputers. We can parallelize our stuff. So let's just do that. And they quickly say, oh, this works very fast. So we'll learn more about that on Sunday from Mohammed, who's the AI expert from RIKEN, and you know more about that. There's a small difference. For one thing, deep learning works very perfectly with, you have to start differently. So when you do calculations, it depends how precise you have the numbers. Is the number behind the comma 10 digits, 15 digits, and so on. And in high performance computing, because the models have to be very precise, we typically use 60, floating point numbers which use 64-bit, 8 bytes of storage. Which is very cost effective, very expensive because you have to lots of data and your multiplication hardware has to work on a lot of numbers. So deep learning can also do it in half a precision or single precision, just 16-bit, or even less. I have people seeing that they use FP8, so just 8 bits. And of course, when they say the single 16-bit is, of course, when you do one simulation with 64, you can do 4 16-bit at the same time. So deep learning is much faster because it's just statistics in basically. And then the other thing is there's many ways of how these different computers talk to each other. But when you look at deep learning, they only need 2 operations. One is called broadcast, which means one processor is sending the data to all the other ones, like sending out spam mail. And the other one is alt reduce. Basically, you get the results of all the processors, and you reduce this one, add them up or multiply them up to one number. So what normal in quotes, like supercomputing, HPC people are afraid of, because now AI is so important that the deep learning people said, oh, we don't need complicated networks. We only need a network which can do these 2 things. And we don't need 64-bit, just give us a computer with 8-bit. And then we simulation people, we cannot use this computer anymore. Yeah, and so this is currently like a little tension between HPC and AI. Yeah, and then, but what we see is, so far in the past years, AI was more from the commercial area, like people like Google, Amazon, Facebook, who want to use like talk to you in TikTok or Google search or something. But now the scientists realize, oh, we can also use it very effectively for doing science. And when you take the two things together, this is basically what most people are currently interested in. How can I combine the data from the simulations and use AI methods to analyze them? Okay, this is what I want to say about AI and HPC, and I leave the rest of the explanation of the API to Mohammed. Okay, so I think everyone has a basic, in this room, has a basic idea what a computer looks like. Yeah, this is how, it's like a very simple picture, but it's enough to understand what's going on. So you have a computer, and in that computer you have a processor. Here it's made in yellow. This is typically called a central processing unit, or CPU. This CPU, meanwhile, can have already a few cores, like 2 to 8, when it's called a multi-core processor, or like with high-performance processors, they can have 128, 192, and then it's called a many-core processor. Okay, then this is basically for the calculations. When you have to store your data, there's main memory in your processor, and it's typically measured in gigabytes or so. And so it can be in 2 different ways. It's typically either dynamic random access memory, or DRAM. You might have heard that name. Or you have very special, expensive ones in servers, which are called high bandwidth memory, HBM. Yeah, and then so this is basically for the calculations in the computing machine, and then for storing all the large data, you do it on a disk or an SSD drive. So we have a disk, which is either a solid state drive or hard disk drive. And then basically this you put in a box or in a little small thing, which basically it's in your laptop, in the screen under the keyboard, and you connect them to a keyboard and a screen and to the network. Yeah, so that's a normal computer. And so, as I said in the beginning, when people want to do parallel computing, what they did is just, okay, they took a few of them. Yeah. So basically, and this was called Beowulf or early clusters. Yeah. So you have this is basically a machine you can buy in a hardware store. Another one, and it depends how much money you have to put together, and you get a switch, an Ethernet switch or something, and you connect them together. And of course, you only need one keyboard to connect to the whole thing. Yeah, and then you use it together, and then you have already a parallel computer. Over time, people realized, like the disk system is kind of in the way here. So what we typically do now, oops, was so fast. What they do now is basically they have actually the compute box, which has the processors, the memories, and they are connected together. And then separately, you have another system with all the disks. Yeah? And so this is basically how modern clusters and supercomputers look like. And on this high level, all parallel computers and supercomputers look like this, more or less. Yeah? But this is basically what you need to know. Yeah? We have multiple processors, we have multiple memories connected together, and in a separate disk system. Okay, now about how to program that. So, what is computation, or when you program? You have 2 parts. You have data you want to process, and you have an algorithm, a method, which does you get the data, do calculations on it, and write out output data. So when we have a parallel computer, we have to do 2 things. We have to take the data and split it up. So each processor gets a portion of the data. And also, in order to make it faster, we take all the things which need to be calculated, and we split the work and give different processors to work on different portions. And then, of course, yeah, like everyone is working on their own, but you want to get one result and you're working on one thing. So typically these processors have to talk to each other. Say, are you done already? Are you done already? Give me your data, I give you my data. Yeah. So it's basically distributing the data, distributing, we call work, to the processes, and then organize and synchronize. And you want to split that up, the data and the work, that everyone is doing more or less the same. Yeah? Because if one gets less, he's done quicker and just sits around and is using energy for nothing. Yeah? So you want to split it up. So the most important or the biggest issue is balancing the load. It's called load balancing. Yeah? Because, okay, but this is the upper part is just the computing. Now I come and says we are doing high performance computing. What does it mean? You do all that, but in the most effective way, using the smallest system possible. So the upper part is already complicated, yeah, splitting up the work and make it way. But when you have in HPC, you have to do it also in the fastest way, as quickly as possible, with as little processors as possible. Because these computers are very expensive, and you should not use them for days, but ideally just for hours. And this is basically where most people struggle and took them years to basically master it. Yeah? So in the beginning, the upper part is not too hard, but that is, yeah, like, as you know, like the first 80% is always simple, and then it takes a lot of things to master the last 20%. So coming back to our little example with digging the holes, yeah, so we have to make a dig a hole. And so we have 4 teams. So we basically split up the area we want to make the hole, and then we have one team making one quarter, another team does the other quarter, and so on. Yeah, and this is, yeah, and splitting up the work means basically everyone gets a different portion of the size of the field, and then and each one gets something to do, and yeah, like some of them do the digging, some of them take the dirt out, and then there's some supervisors who make sure everyone is working and not drinking coffee and things like that. Yeah. Okay. So parallelization. How can I split up a task over multiple processors? There's 2 ways. One is called domain decomposition. So you have a space, like in my last example, it was the hole. So or think about weather simulation. Yeah, you take your map of Japan, and then you make lines, and then each process said you take that quarter and you take this quadratic area, and so you split it up. But sometimes there is no physical, like when you have a map or so, you have a physical thing, but sometimes it's just a virtual conceptual space. Yeah, like some model, but you still can say, okay, I slice it up in different pieces and I distribute with these pieces. And basically this space is called a domain you're working on, and so this is why it's called domain decomposition. You take your space and divide it up. And basically a good example is you have to have a field with strawberries or carrots, and they are planted in rows, and then different workers, like the first worker takes the first row, the second worker takes the second row, so you split up the field, and every worker, which is your processor, basically gets a portion of the field to harvest. The other way is functional decomposition, which means you have typically, first I do this, then I do that, then I do the next step. So you split basically the process up in that way. So the first processor does the first thing, the second processor does the second thing, and the things, like in an assembly line in a car factory, so things move through. So you do a first calculation of some piece, give it to the next one who does the next calculation, and while the second one is doing the second calculation, you take the next piece and work on the first one. So it's kind of like a pipeline of things going through. Now, what do you think is used more? Domain decomposition or functional decomposition? Who is for domain decomposition? No guess. Who is for functional decomposition? And the rest have no idea. Okay. When you think about it, yeah, I said supercomputers are really large and have many, many hundreds to millions of cores. Typically, people use domain computation because they have large data, so large spaces, large domains, and they can split it up in 1,000 pieces or 10,000 pieces. But splitting up things in phases 10,000 times is typically impossible. Yeah, so most people do the domain decomposition because there's so many processing units, and splitting it up in a functional way is hard. Okay, I want to give you like an idea on a very high level by basically say, or basically how does that do by a little mathematical problem. I assume every one of you knows some math, and so you can follow. So the idea is basically you have this formula. Yeah? Y is A times x to the power 3 times b by the power of 2, c by the x plus d. So it's a polynomial third grade. Yeah, and then basically I give you A, B, C, and D. And when I say basically for all x, what is the maximum number? Yeah, so you go basically for all the x's, calculate the formula, remember what is the last highest number, and then the next time it's higher, you remember that one, and at the end, you have the highest number. Yeah, so you just do like lots of calculations for all the different x. So the problem for computers is in mathematics, there are infinite numbers. Yeah, and so our computation would be never finished. Yeah, so what we do is we select a specific set of numbers, and this is when our domain. So we say we take all numbers between -3 and +3, and we take in between, say like 10,000 numbers, which basically, and when we go through these numbers, and because like very close, the numbers are like the maximum is also, yeah, it's typically a function doesn't make like these big jumps, but it goes like this. So we just sample specific numbers, yeah? And so this is called discretization. So you take your real world problem, and then you have to kind of discretize this, but it means you select the region, like the borders from here to here, from here to here, and how fine you want to do the calculation. Okay, so basically this is basically how our computer programs work in normal language. So I'm reading in ABCD with the domain from here to there, and how fine I want to do the calculation. And when I set the maximum to the smallest possible value I can store in a computer, something like -4 million or something. And then I basically go from x min to x max, calculate the polynomial. If that result is larger than the maximum, I store this as a new maximum, and I go through the loop. And at the end, I have the highest number, and I print them out. Yeah, I guess everyone understands that? Okay. So how can we do that now in parallel? So this is the normal program, and this is the parallel program. And everything in blue is extra. You see there's a lot of blue. This is because the actual calculation we are doing is just with one line. Yeah, like just with y something. In a normal parallel computing, you have to do many, many calculations. So basically, like with calculate polynomial, it's typically like thousands of steps. Yeah, and so the blue part is not as much. But for these examples, it looks, yeah, it's a lot. So what you do is, one is something like the leader. For a long time it was called master, And people haven't found a good replacement yet because people think it's not a good word because of master-slave, of course. But ignore that for a moment. So you pick one selected processor, and that processor reads the data from the disk, from a file, and then he uses the network to distribute these values to all the others. So why is not everyone reading the data from the disk? Because reading from the disk is very slow, especially if thousands of processors try to read the disk at the same time. So only one is reading it, and then you have this fast communication network, and then you just say, oh, here's the data to everyone, and just spread it out. Okay, then basically on every processor we do the calculation, but we do it in a way that every processor is doing one portion of that x min to x max. So we take x min to x max and we split it in slices, each of a size of, the distance between x max and x min divided by the number of processors. Yeah? So if I have 20 processors, 20 things to calculate, and I have 4 processors, everyone gets 5 to work on. And then everyone does the calculation, and everyone finds the maximum, but in his space. And when everyone is done, basically the selected processor asks all the others, what are your maximum? And then he does the overall global maximum. Yeah, so basically this is kind of sequential. When you go very wide, as many processors as possible, this is the work distribution. And then this is unfortunately kind of sequential again. One person is collecting it and printing it out. But basically, this is how a parallel computing works. Yeah? You have input and then a lot of calculation, and hopefully this portion is very, very large. And the larger it is, and the more to do, the more effective and the more faster you can do your work with parallel computing. Yeah? So if you try out just a little test example, you never get very fast because you don't have enough stuff to distribute. So this is only good for lots of data, huge problems. Okay, that's it. Parallel programming. What we talk basically in the rest of the section is how to do it in reality. Yeah, this is just on a conceptual level. So the next thing I want to talk about, is how do we know it's high performance? Yeah, so if I'm doing something, how do I know is my calculation effective and is it of high performance? So, and what people do is, it sounds complicated, but when you carefully listen, it's not too complicated. So what I do is, I have my problem, and it has a specific size. Yeah, I have a problem, and I run it on 10,000 numbers. Yeah, okay. Then I write a program to do it on my laptop, run it, and see how long does it take. Yeah, like whatever, half an hour. 1 hour for this problem with 10,000 numbers. Then you write a parallel version of your program. You take the same, like with problem A with so and so many numbers, but you're using processors, 10, 100. And then again, you measure the time. Basically the time on, say, 10 processors, the time on 20 processors, the time on 30 processors, and so on. Okay, and then you define speed up. And what you do is you take the serial time and divide it by the speed up of P is the serial time divided by the parallel time on P processors. Yeah? So say it takes 1 hour, and then on 10 processors it's 10 minutes, so it's 60 divided by 10, it's 6. But we actually use 10 processors. Yeah? So we expect when I'm using 10 processors that it's 10 times faster. Yeah? So what I say, so the speed up, so if I'm getting 6 out of 10, gives me an idea how good I am. The closer I'm to P, the better I am. And the closer I'm to 1, the worse I am. It can be even, the number gets negative, because your parallel computing is, your parallel program is so complicated that it's slower with one processor. Yeah? But normally, the speed up would be between 0 and p. And when other people use efficiency, this is basically the same thing. You say, because in a parallel computer, you use a p processor, so you can do more work. So we divide the serial time to p times the time, because every processor uses the time. But this is basically the same thing. It's just normalized. But instead of going from 0 to p, you go from 0 to 1. And the closer you're going to 1, it's good. Closer to c is bad. Whether you use speed up or efficiency, it doesn't matter. It's both are kind of the same thing. But this basically, people go to a conference, say, I made this weather simulation a new way, and now on 256 processors, I'm getting a speed up of 250. Yeah, and then people have an idea how good he did the parallelization. Yeah, because every time you communicate, every time you just one process is reading something, you lose time. Yeah, because only one person is doing something. Okay, so that's the basic thing you need to know: speed up, efficiency. Yeah, but it's not too hard. Then there is specific words. So I plotted. So here's the number of processors, and this is then the speed up. So if the speed up is a line, so every time I'm using 10 more processors, I get the same improvement. So I get a line, when you call it linear. If it's basically, the speed up is always, like for 10 it's 10, for 100 it's 100, you call it the perfect or ideal speed up. So that's basically the green line. Yeah, but the typical one is like the purple one. For smaller problems, using not so many processors, you get faster and faster, but at some time you run out of enough data or something, yeah, and there's more people than work, and then basically you flatten out, yeah, or you get even worse because they are in the way of each other, yeah. And so basically, when you write your program, you run it on different number of processors, you plot the line, and the more closer it's to green, the better you are. And if it's down here, yeah, then you have to talk to some experts how to get from here to here. Okay. Then there's one funny thing, superlinear speed up. So basically, you're using more processor and you're faster than ideal. So you are using 10 processors, but you are 15 times as fast. How can that happen? There's two reasons. One thing is the algorithm. Thinking about, you have to search a specific book in a library. So you go in a library, the one person, you go first row, up and down, up and down, and down. When you go to second row, up and down, all the way to the end. If you have multiple people, yeah, the first one goes to the first row, the second goes to the second row, and it could be that because the book is on the beginning, yeah, like with 5 people, because the book was in the 5th row in the beginning, you're much, much, much faster. But this is rare. What most in the time happen in this case is, does everyone know what a cache is? Okay, so the memory in a computer is actually two classes. Like my first model was a little bit too simple. So you have a main memory, which is like a few gigabytes, and then it's not read directly into your processor for processing, but it first goes into the cache. It stores it for a few seconds, and then it goes to the memory, and when you basically do the next calculations, it could be you're using the same number again. So it's there in the cache, and it's much faster. But the cache can be read much faster than the memory, but it's much smaller. So it's a few 100 megabyte or something. So at some point, if I split it up, because I use multiple processors, all the data fit in the cache. And all processors can read from a very fast cache instead of a slow memory. And then, of course, at some point, you're getting faster. Yeah? But it's not so important. You can forget about that because it happened very rarely, unfortunately. Okay. Okay, another thing we need to talk about is scaling. Yeah, and this is one of the reasons why it's hard to get a good speed up. So think about, I told you, speed up means I have one problem of a specific size, like a hole of that size. So I do it with one, I do it with 2 people, then with 4, and you see the problem already, yeah? The more people I'm using, but it's still the same small problem, there's nothing left for other people, or they don't even fit, yeah? And so there's a limit, yeah? And so some people in the beginning thought, oh, this parallel computing is a stupid idea, yeah? Because you reach this the space with where everything is crammed in very quickly. And so we should perhaps build a computer with 4 or 8 or 10, but beyond that, it's wasted money. So, but you heard from Satoshi, his machine has, I don't know, forgot, 10 million cores or 1.5, like million. So how does that work? How does that work? Because people said, hey, it's doing it wrong. So if why basically keep this problem there? If I have 2 people, we can make a hole twice as large. If I have 4 people, I can make a hole 4 large. So the idea is basically, again, I'm scaling, so I'm using more and more processors or workers, but the more processors, I also can work on larger data. Yeah, and then it doesn't have to be double like here, but it basically, yeah, like you have a specific function over time where the more processors you use, the more data you're processing. And this is called weak scaling. But again, you say, okay, yeah, going from 1 to 4, I get a speed up of so and so. So what you have to report is if you're using this method, the weak scaling method, you have to describe like what is the scaling of your data. Otherwise it's unfair, yeah, because people think, oh, you did the complicated way. But as long as you say it's weak scaling, I'm scaling in that way, the speed up is fair to report. Okay. That's basically about, there's more things, but this is as a starting, the most important things. And then we also want to get another high-level number, how good a program is and how fast a computer is. And this is basically because most calculations are a calculation on a floating point number. Yes, 1 dot something, but to the power of 10. And you just basically say, how many of these floating point calculation I can do in a second? Yeah, because it's floating point operations per second, it's a flop. And then in the second is flops. So in normal life, a flop isn't really a bad thing. But in high-performance computing, the more flops you have, the better. It's, yeah. Computer nerds are always different. So meanwhile, we have these computers can do so many flops that we have to use these international prefixes. Yeah, like kilo is 1,000, mega is 10,000, and there's tera, peta, exa. So the current fastest computers in the world, there are 4 of them, they can do 10 to the power of 18 or a quintillion number of operations in 1 second. I can give you a good picture what that means. Quintillion, I can. With a million, I can kind of imagine what it is, but I have no idea how to explain a quintillion. It's an enormous, huge number. Like it's mind-boggling. Okay, the thing. Yeah, like people like me, yeah, said, oh, in Jülich, where I'm coming from, we just installed Europe's first exascale computer, exascale. We are great and big. Yeah, when you listen to people like me, you have to be careful. There's a few things. The devil is in the details. So I really ran a program and I measured that I got an exaflop operation per second, or did I just some modeling, say, okay, that processor can do this, it has so and so many units, it runs at that speed. So is it a theoretical number, or is it a real number? I can assure you in Jülich it's a specific program called HPL, High Performance Lint Pack. We ran it and we got 1.00 exaflops. Okay, then basically does that program only count the useful operations which I needed for the calculation? I could just run a program who just said +1, +1, +1, +1. So it never does anything useful. Then of course I get a huge number, but this is not useful. So it should be something useful. Then I told you the precision. Is it 64 precision or less? So for this, what the number we measure is typically 64-bit. And for AI, we get larger numbers because they have smaller. Yeah? They up to a few, 80 exaflops already. Then there's other specific things. Some processors can do a float and a multiply at the same time. So we say we multiply a number and add a third number as one step. So is that now counted as 1? Or as 2, because it's a float, and. So some people have different opinions on that. And so basically this is the things to watch out for. But this is what the 3 things I want you to remember. There's speed up and efficiency, then strong and weak scaling, and then another one is measure number of floating point numbers, and this is typically what people typically use. Yeah, and then of course also for I/O, how quickly can I read numbers and things like that.